let's go ahead and start. Today we're doing chapter 27, which is 2 sample tests. So what we've done before is we did just 1 sample and looked at the averages. Now we're going to do 2 sample tests. We can also use this for controlled experiments. With 2 groups of people. So it turns out that the same equations can be used for either situation, where you have 2 samples from the population or you have a controlled experiment with 2 groups. So for our first example, we have one semester, a statistics class has 600 students. There are 2 versions of the final exam, version A and version B. The finals are graded, and it is found that the average score for the 300 students who got version A is 67, with a standard deviation of 21. The average score for the 300 students who got version B is 77, with an SD of 20. Assume that each student got version A or B at random, and that both versions were graded comparably. So this is actually one where you can think of it as a controlled experiment with the 2 groups, because they had the entire statistics class, and then everyone in there was kind of randomly assigned to version A group or version B group. And now we want to compare it and see which version was harder. So our first question is asking, is there evidence that version A is more difficult than version B? And whenever I do these, I'm going to start by writing down the information they give me. So for version A, there were 300 students. So my sample size equals 300. The average is 67. And the standard deviation is 21. Now for version B, we again have a sample size of 300. My average equals 77, and my standard deviation equals 20. Once again, this is what I do on all of my tests. I write down the information they give me first, then our next step has always been look at the null and alternative hypotheses. Okay. Although first, we should check if we can do the test. Does anyone remember what the requirements are to do a 2 sample test from the video? How do we tell if we can do that test?
We have a sample SD.
Okay, that was to do the t-test, we needed a sample SD. Now just to use the 2 sample test. To use a 2 sample test, we need either both have large sample sizes, meaning at least 30, so at least 30, or are normal. Now in this case, both of my sample sizes are large, so we're good to go. Now you need to check that for both samples, so either both sample sizes are large or both sample sizes are normal or some combination. Then you come up with your hypotheses. So the null hypothesis, if you think about status quo, nothing interesting, that would be that your 2 versions are the same. So version A and version B are the same difficulty. And that would mean that, yes, we did see some differences in the averages. So this is saying, well, they're the same difficulty, the differences were just due to chance, because you always have some chance error that comes into play. So this whole test is telling us, okay, is that 10-point difference, is that just due to chance error? Or is maybe version A really easier than version B? So the null is that they are the same difficulty, and that any difference is just due to chance. The alternative, we wanted to see, is version A more difficult? So version A is more difficult. Now we say this because for some reason the teacher thought ahead of time that version A would be more difficult. That was the hypothesis she came up with, was that it was more difficult, so this is the hypothesis we're going to test. Now we want to come up with our test statistic. First we need to find the standard errors for both of the individual versions. So we'll find the standard error for A first, and standard error, once again, is your SD over square root of your sample size. The SD that we're interested in for A, the SD is 21, the sample size is 300. So 21 over the square root of 300. So 1.21. We also need to find the standard error for B, for version B. So that SD is 20, and that sample size is 300. So these standard errors are actually very similar. So 1.15. The reason we need those is our test statistic is Z equals the sample average for A minus the sample average for B over the square root of the standard error for A squared plus the standard error for B squared. So let's plug everything in. The sample average for A, the average is 67, minus the sample average for B of 77, or the square root of my first standard error is 1.21, and we'll square that, plus my next standard error of 1.15 squared. So everyone go ahead and make sure you can put this in your calculator. It might be difficult to get the correct answer. A few things: make sure you have everything inside the parentheses, or inside the square root needs to have parentheses, and everything on the top needs to have parentheses. So it kind of looks like this. I'll add in red where you're going to need your parentheses. So I got Z is negative 5.99. Anyone else? Everyone else, I guess make sure you get that same answer. Now you might have noticed that when I wrote down my information, I chose to write version A first, mostly because that was the order it came in the problem statement. And because I wrote version A first, then I found like the standard error for A first, I wrote the sample average for A first, everything I did with A first. Now I want to go and find the p-value. The hardest thing I think about these tests, the two sample tests, is trying to figure out which direction to shade. So here's the thing. We had A minus B. That was the order we wrote them in. Okay, now according to the alternative statement, remember, you look at the alternative statement to decide which way to shade. We said version A should be more difficult. Now, more difficult means version A has blank scores. So if version A is more difficult, should version A have lower scores or higher scores?
Lower.
Okay. It should have lower scores. Oh, version A. Forgot the A there. Let's see. So if I do A minus B, I think of it this way. So I say A is supposed to be small numbers, and B is supposed to be big numbers. Now for this, think to yourself, okay, if I take a small number and I minus a bigger number, am I going to get a positive or a negative? So like 3 minus 10 would give me negative 7, right? So if I do something small and minus something bigger, I'm going to get a negative result. And if I'm hoping for negative results, because I'm hoping that A is smaller, I'm hoping I get negative results, so I'm going to want to shade to the left. If I was hoping to get positive results, then I would shade to the right. So I say, okay, here is Z equals negative 5.99, and I want to shade to the left. Now, without even looking it up on the table, what would you tell me this should be? Okay, let's look it up then. So I'm looking for negative 5.99. So yep. So here's my negative 3, negative 4. So you said basically 0. So negative 5.99 is going to be way up here. So that area is going to be basically 0. So this area is basically 0. So my p-value is basically 0. That, of course, is going to be a small p-value. Because it's a small p-value, I will reject my null. Just like everything else we do, we follow the same steps. So small p-value, reject the null, and now we have evidence for the alternative. So we have evidence that what? Version A is more difficult. So I have evidence that version A is more difficult. So A's scores are lower on average. So we said, okay, yes, that 10-point difference, that wasn't just due to chance error, but it's evidence that version A really was more difficult. And finally, in part 2, would your test still be valid if the exam scores didn't follow the normal curve? Well, if you look back up to our check, we said both have to have large sample sizes or follow the normal curve. And both of our sample sizes were large, so we don't need it to follow the normal curve. So yes, because we have large sample sizes, it is okay if the scores do not follow the normal curve. Because we only needed large sample sizes or normal data. And the deeper theoretical statistical reasons behind this is that the central limit theorem tells you that all of the possible averages follow the normal curve, and then it turns out that any differences, so if you do like sample average for A minus sample average for B, all of those differences will also follow the normal curve if you have a large sample size. So last one, test. Again, hopefully you watched the video first, so this isn't coming out of nowhere. What questions do you have about doing this test? Anyone?
We're good in Twila.
Okay. I guess let's try the next problem. So researchers think that eating margarine lowers the particle size of LDL molecules, so-called bad cholesterol, compared to eating butter. In a randomized controlled double-blind experiment, okay, so notice this one even tells you that it is a controlled experiment situation. 105 people in the treatment group, the margarine diet, had an average LDL particle size of 252 with an SD of 4.5. While 110 people in the control group, the butter diet, had an average LDL particle size of 254.8 with an SD of 4. Perform a test to determine whether the researcher's claim is correct. You have to state a null and alternative, compute your test statistic p-value, and clearly state your conclusions for people on margarine and butter diets such as those in this study. And this is the kicker, I don't think we've done this yet in this class. I want you to use the cutoff significance level of 1%. So for this one, we don't want it to just be 5% for our cutoff level. We want to be really sure, and so we're going to do a significance level of 1%. Just kind of for practice so you can see what happens if we change that significance level. Let's start by writing down our information. So we have our treatment, or our margarine, has, let's see, my sample size of 105 people with an average of 252.6 and an SD of 4.5. The butter diet people have a sample size of 110. An average of 254.8 and an SD of 4. Now, did you guys notice on the video in this one that sometimes my sample sizes are different between the two groups? That's okay. There's absolutely nothing wrong with that. Now we should also check that we have both large sample sizes or normal data. So do I have one of those in this situation, and which one?
Large sample size.
Okay, we do have large sample sizes for both of them, and so we can go ahead and do this one. Then my null hypothesis, the null will always be that your two groups are equal or are the same. And so in this case, the average LDL size is the same for margarine and butter diets. And then for the alternative, so now we need to go back through and look and see specifically what they want us to test. Let's see. Oh, the researchers specifically think that eating margarine lowers it. So they think margarine particles, or the margarine should lead to smaller particles. So the average LDL size is smaller for the margarine diet. Now my next step is to find the test statistic, but there's usually some intermediate work that we need to do. In this case is find both standard errors. So let's find the standard error for margarine. And remember, it's just always your SD over square root of the sample size. The SD for margarine is 4.5 over the square root of the sample size, which is 105. So 0.439. Now you might have noticed that I haven't really been distinguishing for this chapter between the sample SD and the population SD. And the reason why is technically, just like for our one sample where we have a z-test or a t-test based on whether it's a sample SD or a population SD, the t-test for two samples is pretty complicated, more complicated than what we want to do in this class. So for this class, we're just having you do just the z-test, and so we're just kind of ignoring whether it's a sample or population SD. In practice, you would just run it on the computer, and it's very easy. But doing it by hand is very complicated. We're talking like 5 to 10 minutes extra of computation. So we're just skipping that, and so we're not really bothering distinguishing if it's a population or sample SD. And standard error now for butter, its SD is 4 over the square root of its sample size of 110. So 0.381. Now we can do our test statistic. Of Z is going to be my sample average. And just because I wrote butter first up above, I'm going to write, sorry, I wrote margarine first. Because I wrote margarine first, I'm going to continue writing margarine first. So sample average for margarine minus sample average for butter. Over the square root of the standard error for margarine squared plus the standard error for butter squared. Now, if you write it in a different order, so if you do butter minus margarine, that's okay. You're just going to get, like, if I get a negative, you'll get a positive and vice versa. But because you write in a different order, you'll also shade another tail, and so we'll end up getting the same results as long as you do your work correctly. Okay, so sample average for margarine was 252.6. Sample average for butter is 254.8. Now I'm just looking at those two numbers, and remember how we said before that just because it makes a difference to us statistically, it might not make a difference in the real life. It might not really be practically significant or really important to us. And I'm just looking at these two numbers, and I don't even know yet what kind of p-value I'll get. But 252.6 and 254.8, those don't seem very different, right? At least to me. And maybe that would make a big difference, but if you're already in the 250s, it doesn't seem like 2 is really going to make a big difference. So maybe this would be a case where even if we do get statistical importance, maybe it really wouldn't be practically significant. Maybe we wouldn't really care. It wouldn't make a difference in the real world. So that's just a side thought. Let's go ahead and continue on with our problem. So square root, so standard error for margarine, we said was 0.439. So we need to square 0.439 and square 0.381, and then we add those two together. And once again, make sure you can put this in your calculator. To put in your calculator, you're going to need parentheses around everything on the top, as well as parentheses around everything inside the square root. Or you can always do the top and bottom in separate steps if that's easier. Now it's time for the p-value, but first we have to figure out what direction do we want to shade it. And so for this I come back once again and I say, okay, I did an order of margarine minus butter. So margarine minus butter. Now let's go back to the alternative to see which one is supposed to be smaller or bigger. So the average size is supposed to be smaller for margarine. So technically this should be small numbers minus big numbers. And then you're trying to figure out if that should give you positive or negative results. So small numbers, say if you had 3 and you minus 10, once again you'd get negative 7. So we're expecting negative results, and anytime you expect negative results you would shade left, since that's where the negative numbers are, to the left. So here is z equals negative 3.78, and I'm shading to the left. Let's look at the normal table. We're looking for negative 3.78. So this negative 3.80 is pretty close. So the area to the left is 0.0072. So my p-value is 0.0072%. That is a very small p-value. And so, now when I say it's a small p-value, I'm just kind of saying it is very small. Specifically, it is smaller than 1%, because we wanted to use a 1% as our cutoff for this problem. So we will reject our null. And now we have evidence and not only evidence, but lots and lots of evidence, because that's a really small p-value, lots of evidence that on average the LDL particle size is smaller for people on margarine diets. Now, once again, so let's just go over that side note again. So, because the p-value is small, we have statistical significance. Meaning we are sure, statistically, that there is a difference. but this difference might not be practically significant. So a difference of, let's see, what was the specific difference? 25.2 minus 254.8, that's a difference of 2.2. So a difference of 2.2 might not matter in the real world. I'd have to ask a doctor. Once again, there's a difference between statistical significance and practical significance. Statistical significance just means we're sure, statistically speaking, that there is a difference. Practical significance means, is that difference big enough that we would actually care in the real world? And statistics can't answer that. You have to go ask an expert in the field, or ask yourself if it would matter to you personally. How about questions on this one?
Can you just show a little example, like on the p-value part, if it was positive? Just so
If my z-value had been positive?
Like if we decided the shade did it right, what the p-value would have.
Okay. So our question is, what if we decided a shade to the right? So specifically, if I still had the same z-value and I shaded to the right, then this p-value would be 100% minus 0.0072%. So it would be 99.9928% if we wanted to shade to the right, and our z-value is still negative 3.78.
So I'd just say like big minus small, and that would be positive, and the change in the right?
So what I want to do to answer your question is, let's open up a new page and do this problem. Let's go back a little bit and do this problem from a different angle. So let's do this problem. So what if I did butter minus margarine? So my null and everything stays the same. My standard errors stay the same. But then when I try and find z would be my sample average for butter minus sample average for margarine. So everyone go ahead and follow along with this on our computation so you can see what does happen if you do it in a different order than I do. Because I think it's always good to see this one. Over the square root of my sample error for butter squared plus the standard error for margarine squared. So I'm going to just read these off my paper. So the sample average for butter is 254.8. Sample average for margarine is 252.6. And the standard errors we said are 0.381, and I don't remember the other one, 0.439. So everyone go ahead and put this one into your calculator to see what you get. So I got positive 3.78. So what's the difference between these two problems? Here I got a negative 3.78, but when I switched the order I subtracted, I got positive 3.78. Then for the p-value, okay, now I did it in a different order. So now I did butter minus margarine. So I still go back to my alternative hypothesis, and I'm still trying to show that the margarine is smaller. So margarine is supposed to be smaller. So in this case, margarine is small, so butter must be the bigger one. So we're going to do bigger minus smaller. So now if you're doing big numbers minus smaller numbers, if you do like 10 minus 5, you're going to get positive numbers. And anytime you get positive, you'll shade right. So here's my positive z equals 3.78, and I want to shade to the right. Now see how just due to symmetry, this is going to be the exact same p-value. But if we hadn't already done it, I could look it up on my normal table. So I look up 3.78, or this 99.9928. I forgot what I said again. 9928. So I'm going to have to use the fact that everything adds up to 100%. So 100 minus 99.9928% gives me 0.0072%. So my p-value is 0.0072%. So you see how if you do decide to subtract in a different order than me, you'll just get a positives or negatives will be swapped, and you swap which side to shade, but your p-values will end up being the same. And then from there, you say it's a small p-value, you reject, and your conclusion is exactly the same. So other thoughts or questions on this one? Then I know we're still slightly early, but we're about halfway through. So let's go ahead. What I want you to do is I want you to try the next problem. So take about 5 minutes to try the next problem and see how far you can get. Then you can take your 5-minute break. So we'll meet back here at 6:05 to compare our answers. So do the next problem first, see how far you can get, then we'll come back and compare. Start again. Now that I've fixed my conclusion and I have it correct. This is why it's always good to have double check your work or have someone else do it. So I started this problem. Okay, one of the first things I noticed is they did give me the summary data in a nice little table, but they forgot to tell me the sample size. Each sample size was 50. And I did want to check, did I have either both large sample sizes or normal data, but both sample sizes were 50. That counts as big, so I can do this test. The null hypothesis would be that on average type A and B remove the same amount of particles so that they work the same. The alternative is that on average type A removes more particles than type B. So type A would be better. And I had to find each standard error by the SD over the square root of the sample size. And then for my test statistic, I just did A minus B. So I ended up with the test statistic of 1.15. So any issues getting to this test statistic of 1.15? And then for my p-value, because I did A minus B, I have to figure out which direction is shade. So A was supposed to be bigger or remove more p-value or more particles. So that was a big minus a small, and anytime you have big minus small, you should get positive. And if you're expecting positive, let's shade to the right. So here Z is 1.15, and we want to shade to the right. And that gives me an area of 12.51. So I even wrote that one wrong. Transposing numbers in my head. So my p-value is 12.51%. Now that's a big p-value because it was bigger than 5%. And when you have a big p-value, you fail to reject your null hypothesis. Oh. And I deleted my conclusion.
Question?
Yes.
So, how do you know which number to put first when you're finding, like the p-value, for example, this one you did A minus B, and the other one you did margin minus butter first. How do you know which one to do?
Okay.
If that makes sense.
Yeah, it does. So for you, it doesn't matter until you write down what you're going to do for Z. So I can choose if I want to do sample average of B minus sample average of A, or sample average of A minus sample average of B. And at this point, it doesn't make a difference. Okay? But once you write it down here, then you have to keep that order for the rest of the problem. So because I wrote a minus b, I have to figure out, for my p-value, I have to do a minus b, big minus null, etc. The way I do it is I just, whichever one I wrote down first, that's the order I keep, and I always do that one first from here on out. Okay, but it doesn't really matter until you get to here. Once you write it down, though, you're stuck with that order for the rest of the problem.
Okay, thank you.
Yep. Okay, and since we failed to reject the null, that means we didn't find enough evidence to conclude that filter A removes more particles on average than filter B, or no reason to think that filter A is better. Now, just as an interesting side note, so you might have noticed the first two that we did were both kind of controlled experiments where you had your group of people and you split them into two groups and assigned one group treatment A or treatment B, things like that. This one was slightly different in that we had two types of water filters that we wanted to compare, and 50 filters of each type were tested. And so this one was kind of one where we had a big supply of filters and we took random samples, versus having a big group of people and splitting them into two groups and giving them treatment. So this is one where you can think of it as random samples. Whereas the previous two examples, the margarine one was a controlled experiment with two groups, and the first one was also a controlled experiment with two groups. And if you remember, we did talk about kind of our controlled experiments versus random samples in the second video. So the first two were examples where we had a controlled experiment and we split the people into two groups. And the next example is more of one where we had random samples from a bigger population. And so on example 127, a statistics teacher wants to see if the abilities of students enrolled in statistics today are less than those enrolled 5 years ago. A sample of final examination scores from students enrolled today and from students enrolled 5 years ago was taken, and here's the following information. And so this one again is kind of the random samples from bigger populations. Now at this point, that is a little more technical than you need to get into because again, the way you do the test is exactly the same. So for this example, it's written in multiple choice format, so you can get used to seeing it that way. And I gave you all this information in a nice table format. Now, if you remember, the way I like to do these multiple choice problems is I'm going to go ahead and work everything myself, and then I'll go ahead and compare it to the multiple choice answers. So first, let's check, and we need large sample sizes or normal data. And on all the ones we've done today, they've all been large sample sizes. So this one is 45 and 60. That does count as large samples, so we're good. Then the null would be that the scores, yes, final exam scores. The average scores for all the students 5 years ago and the average scores for all the students today would be the same. So no difference. Null is always that they are the same. So the average for all students today and all students 5 years ago is the same. And then the average, let's see, she wants to see if the abilities are today are less. So the average today is less. Let's find both of the standard errors. So standard error for today is SD over square root of sample size. My SD for today, 10.6 over the square root of 45. One of the things you want to make sure you do for these problems is put the correct SDs with the correct sample sizes, so don't kind of mess up your two groups. And the SE for 5 years ago is the SD of 7.3 over square root of its sample size of 60. So 0.94. Now Z equals, so for which order to do it in, I'm just going to do today first, just because today was written first in the information. So it's going to be sample average today minus sample average for 5 years ago, or the square root of standard error today squared plus standard error for 5 years ago squared. My sample average today is 82. Minus average 5 years ago was 88. Square root, and my standard errors are 1.58. So I'll square that, and 0.94. And I'll square that as well. So negative 3.26. And again, I'm just kind of continuing on. I'm going to work the entire problem and then go back to try and pick the correct answers for the multiple choice. So my p-value, we did today minus 5 years ago. Now she says she thinks today's students are less, their abilities are less, so their score should be less. So today should be smaller, whereas 5 years ago should have been bigger. So we have small minus big, so we're going to be looking for negative values. So we'll shade left. So if I look up negative 3.26, that area to the left is 0.0577. So my p-value is 0.0577%. That's a small p-value. I'll reject the null, and I'll have evidence that today scores are less. Now that we've written everything down, let's go back and select our final answers. The test statistic is z equals negative 3.26, so C. The p-value is 0.0577. And we said she should reject the null. Now make sure on number 3 that you reject the null instead of rejecting, say, the alternative hypothesis. It's always reject the null or fail to reject the null. It's always about the null. And as you read through the 3 options for number 4, which one do you guys think that it should be?
C.
Okay. I agree. We said we have evidence that today's scores are lower, so it's likely that the abilities of students today are lower than the students 5 years ago. So that's what we have for our 2 sample tests. It's basically we learned one new formula, did it over and over again. What questions do you guys have? Then we are officially done with our lesson today, so I'll be around and you can stick around and ask any questions from the homework or anything else.
I would just like to say this was very helpful tonight, so thank you.
Good. Made more sense after doing some problems? Good to know.